In this video, I will discuss mass and weight. Before watching this video, I recommend you to watch the video on inertia and Newton's first law. We have mentioned earlier that the weight of an object is a force, the force of a gravitational attraction of the Earth or whatever astronomical body the object is near, such as the Moon or Mars. Now we will later talk about gravitational interactions in detail, but we need some discussion, primary discussion now. The terms mass and weight are often misused and interchanged in everyday conversation. It is absolutely essential for you to understand clearly the distinctions between these two physical quantities. Mass characterizes the inertial property of an object. The greater the mass, the greater is the force needed to cause the given acceleration. This meaning is reflected in Newton's second law, which is sum of the forces equals mass times acceleration. Weight, on the other hand, is a force exerted on an object by the gravitational pull of the Earth or some other astronomical body. Everyday experience shows us that objects that have large mass also have large weight. For example, a cart that is loaded with the bricks is hard to get started rolling because of its large mass. And it is also hard to lift off the ground because of its large weight. On the Moon, the cart would be just as hard to get rolling, but it would be easier to lift. So what exactly is the relationship between mass and weight? The answer to this question, according to legend, came to Newton as he sat under an apple tree watching the apples fall. Apples fall. A freely falling object has an acceleration a with a magnitude equal to g. So as the apple falls, it accelerates. An acceleration has a magnitude of g. That equals 9.8 meters per second square on Earth and 6 times less on the Moon, for example. We can get this acceleration to equals 9.8 because the apple is just in a free fall, and a free fall is due to the gravity of the Earth. And because of Newton's second law, this acceleration requires a force. So for which is the Earth is forcing the apple to fall. That force, according to the Newton's second law, should equal the mass of the apple times the acceleration. If we assume that the object, in any object, has a mass of 1 kilogram, and it is falling freely, acceleration would equal g, that equals 9.8 meters per second square, then the required force must have a magnitude of 1 kilogram times 9.8 meters per second square, which is 9.8 kilograms times meters per second square. This is the time to say that kilograms times meters per second square is named in honor of Newton as a unit, SI unit for the force, and it is Newton, which equals 9.8 Newton. Now, we know that the force that makes the object accelerate downwards is the gravitational pull of the Earth. Watch my video on catalog of the forces. So that gravitational force, gravitational pull of the Earth, is the weight of the object. Any object near the surface of the Earth that has a mass of 1 kilogram must have a weight with the magnitude of 9.8 Newton. So pretty much the weight, this force is actually the weight of 1 kilogram object. In other words, 1 kilogram object has a weight of 9.8 Newton. Now, if we start from a Newton's second law and substitute the force with the notation with the weight and acceleration with the g, then we can say, well, what I'm doing this is substituting in here. I would say the weight equals mass times g. And we can put the vector notation on this. And for the vector notation, that would be weight equals mg. Because of the weight is a force, we can write this equation in terms of a vector component because it's always going downwards. And if you consider the negative y going down, positive y going up, then your the y component of the weight equals negative mg. Thanks for watching. Stay tuned for more to come.